Inserting 3D objects into a 2D image is a vital task with a wide range of practical applications. For example, when you want to draw a comic, you can incorporate 3D objects into the background drawings. In the case of interior design, you can use the picture of your room to preview how new furniture will fit and appear. Or, for product mockups, you can visualize prototypes in various settings. However, when it comes to composing images in those scenarios, for seamless integration, you have to consider various parameters including the perspective, lighting, and color grading. Let's look at the most trivial and straightforward way to insert a 3D object into an image. That would be exporting the 3D object as a 2D image with transparent background, and then you can overlay that on top of the source image. Finally, you can adjust the lighting, shadows, and colors. While seemingly simple, this approach is time-consuming and requires extensive editing work. It is also not optimal if you want to rearrange the 3D object, such as position, scales, or the rotation. Or if you want to add more 3D objects, you have to redo the adjustment. So, let us introduce our approach. Instead of working in 2D, we first reconstruct the image as a 3D geometry. Then, we proceed to estimate the light sources that emulate the lighting conditions in the original image. Finally, we add the 3D objects into the 3D reconstructed scene. Since they will directly interact with the scene, even when the objects get rearranged, the overall rendering will be processed dynamically. Now, let's break it down further. This pipeline consists of the following steps. First, it runs intrinsic decomposition with the downscaled image. By doing so, we obtain the albedo and shading of the input image. Next, it estimates the 3D geometry using Moji. Using the output and albedo, it then constructs a 3D scene using Mitsuba. Then it estimates the light sources based on the user's initial guess. Through the GUI, the user marks where the light source might exist on the input image. Point lights are then placed based on the 3D positions and normals of the corresponding pixels marked by the user. Then, the intensity and positions of those lights get optimized using Atom. The user then inserts the object and can readily modify its position, scale, and rotation. In the final rendering step, an alpha mask is generated to delineate the pixels affected by the inserted 3D objects. This mask is then utilized to composite the rendered output onto the input image, ensuring the preservation of the original quality in the unaffected area. Here is the image composing in action.
Now let me demonstrate our application. We first load an image. Then we can mark the light source here. This step is optional. If you don't mark the light source in the image, our program can estimate the light source automatically. Then we click Start. Our program will estimate the geometry, shading, and albedo, and also the light source of this scene. Now we get a preview image. We can click the objects on the left-hand side and click the image to insert our object. We can further adjust the configuration of this object. To get the final result, we click on the render. This will give us a high-quality rendered image. Finally, we click on Download the result to download. That's all. Thank you.